Hello everyone, welcome to our differential equation class. In this video we are going to focus on 2x2 systems of linear differential equations, and we are going to start with a brief review of the main definitions that we need. Then we are going to introduce the system we are interested in, which are diagonalizable systems. Recall we are working with 2x2 systems, and we are going to find solutions for these systems in two cases. In the case that the matrix of coefficients has real and different eigenvalues, or it has complex eigenvalues. It doesn't matter which case, we are going to obtain solutions for systems 2x2 that have a diagonalizable matrix. So that's the plan for today. Let's start with the main definitions that we need today. For example, what is 2x2 systems of first order linear differential equations? Well, here it is. A 2x2 first order system of linear differential equations is an equation of this form, where we have put all our variables in the vector x. X in this case has two variables, the two components x1 and x2, which are function of times. These are the functions we are trying to find, solutions of this equation. All the coefficients of the system are in the matrix of coefficients, that in this case is a 2x2 matrix. The coefficients in general can depend on time, but we are going to focus today on constant coefficient equations, so there's not going to be time dependence here. And then we can have a source vector b that has two functions, b1 and b2, as components, and today we are going to focus on the case that we don't have this source vector, so this is 0, and this matrix is a constant matrix. So all these definitions are written down here. Oops, there it is. For example, we call equation 1, which is this equation, we call the equation homogeneous if and only if we don't have this term here. Then we call this equation of having constant coefficients when the matrix A is constant, so there is no t dependence here, and the system is diagonal when this matrix is diagonal, and the system is diagonalizable when the matrix A, matrix of coefficients, is diagonalizable. The other definitions we are going to need today is, well, not definitions, that the main result from a previous video is that if you have two functions, x1 of t and x2 of t, that with the property that they are not proportional to each other, and these two functions are actually solutions of an equation of this form, which is a 2x2 system of first order equation that is homogeneous and with constant coefficients, then if you have these two functions, x1 and x2, then every solution, any other solution of this equation, equation 2, can be written as linear combination of these two functions, x1 and x2. Recall, they are solution of the equation and they are not proportional to each other. This is called the general solution theorem, and the functions x1 and x2 with that property, x1 and x2 with being solutions and not proportional to each other, they are called fundamental solutions of the equation. The fundamental solutions are not unique, there are many fundamental solutions, but any two functions with this property, they are called fundamental solutions. And this equation here is called the general solution of the equation, because it includes all the solution of the equation. And another thing that is useful to remember from a previous video is that every second order linear differential equation, something of the form y double prime plus a1 y prime plus a0 y equal b of t, any equation of this form can be written as a 2x2 first order system of equations, like this one. for appropriate choice of the variables. One last remark is that, this is a simple remark, is that diagonal systems where this matrix here of coefficients is a diagonal matrix, these diagonal systems are very simple to solve. And we are going to see that in an example. So consider this system x prime equal ax is homogeneous because there is no b and constant coefficients, and in particular the coefficient matrix is diagonal, which means only the elements in the diagonal are different from 0, all the other elements are 0. And well, this system is very simple to solve, as we are going to see right now. For example, let's put the solution over here. Solution. Well, the system is, let's write down the system. The system is, let's write it down explicitly. X has two components, so let's call it x1 and x2. Then we have the derivatives of these two components in a vector, and this is equal the matrix of coefficients, which in this case is the matrix 3, 0, 0, 2, acting on the vector of variables x1 and x2. This is our system. Well, but if we do this matrix vector product, we are going to get here 3x1, and in the second component we are going to get 2x2. So this is a very simple vector, which is 3x1 and 2x2. So from here we see that the two equations that we have are really simple, and let's put it maybe over here. The two equations are, the first one is x1 prime is equal 3x1, and the other equation x2 prime is actually equal to x2. Well, these equations are what we call decoupled, so let's write this down. These two equations are decoupled, kind of ugly E, decoupled, because the equation for x1 does not contain, there is no x2, and the equation for x2 there is no x1. So we can solve the equation for x1 independently of the second equation, and we can solve the second equation independently of the first. And the solutions are very simple, because this equation, both of them, are actually the exponential growth equation. So we have learned how to solve this equation long time ago in one of our first videos, and the solutions are x1 of t is equal some constant that we are going to call c1 exponential 3t, and the other function, this one over here, is x2 of t is some other constant, which if you have initial condition you can fix them, times exponential 2t. And that's that. These are the solutions. So that's the problem. As we said, diagonal systems are very simple to solve, because the equations are what we call decoupled. You can solve one equation at a time. We have a little remark here that it could be useful. It could be very useful if we write the solutions in vector form. So let's try to write the solutions in vector form. The solutions we have here. Okay, if we write it in vector form, what do we get? Well, let's start here. X of t, recall, is a vector that has on each component x1 of t and x2 of t. And we found these functions. So the first function is proportional to the exponential 3t, and the other is proportional to the exponential 2t. Okay, nothing interesting going on here, that's the vector, but let's write the vector in the following way. Let's write this vector as the first component, c1 exponential of 3t, 0 over here, plus the other component, which is 0 over here, c2 exponential 2t. And now let's do something else. Let's move these constants away from the and leave a vector as a constant vector. So we are going to have c1 over here, the vector 1 0, and yeah, let's make it a little bit longer, a vector 1 0, and then exponential 3t plus c2, so c1 and c2, recall, are arbitrary constants, then the vector 0 1, and then exponential 2t. Okay, that is more or less where we wanted to, how we wanted to write the equations. And now let's notice something that is going to be useful in the future. Here we have our coefficient matrix 3 0 0 2. This matrix has eigenvalues and eigenvectors. The eigenvalues are the first eigenvalue is 3, and the corresponding eigenvector v1 is the vector 1 0. And the other pair is lambda 2 is equal to, and v2, the second eigenvector, is 0 1. Okay, and here this is the reason for the remark. Notice that the solution, the general solution of the equation with this coefficient matrix has this vector in there, and this vector is one of the eigenvectors, and the corresponding eigenvalue is right there in the exponential, multiplying that vector. And then for the other term, we have this vector here, and this vector here is exactly the other eigenvector, and is multiplied by an exponential that has precisely this eigenvalue. So this is not a coincidence, and actually it's going to happen in more complicated systems that we are going to study right now. So we just remark that when you write the solution in this way, you don't notice until you write the solution in vector form, and then you decompose the solution and have this very peculiar form that relates the solutions with the eigenvalues and eigenvectors of the coefficient matrix. This is no accident, and we are going to see it pretty soon. Why it's not an accident. Let's move on to the main systems we want to study in this video, which are diagonalizable systems. And why we are interested in this type of systems? Well, one reason is they show up in many applications, in physical applications, and the other reason is that they are very simple to solve, because diagonalizable differential equations can be transformed into diagonal equations for a new variable. And once you have a diagonal equations, as we saw in the previous example, we know how to solve them, and then we can transform back the solution of the diagonal equation into the solution of the original equation. Here is the main result that we can write about this. Suppose we have a 2 by 2 matrix, let's call it matrix A, that is diagonalizable, and if it's diagonalizable, that means we can write matrix A as a product of P, D, P inverse, so matrix P is invertible, and D is diagonal. Suppose we have that. Okay, the first result is the following. The vector function x of t is going to be solution of this equation, a 2 by 2 system of linear differential equation that is homogeneous and constant coefficients, if and only if the following vector function y of t, which is p inverse x, where here is p inverse, x is solution of this equation if and only if y is solution of this equation. And this equation is a 2x2 system for y, but has a diagonal matrix as a matrix of coefficients. So we know how to solve the equation for y. So this is the first result. For diagonalizable systems, we can always solve an equation for y, which is diagonal, and then we can transform back. And if we transform back, for example, to transform back, we need what is the expression for p and d. Suppose p is given by v1 and v2 and d by lambda 1 and lambda 2. We know from previous videos that when p and d are written in this form, then lambda 1 and v1 and are eigenvalues and eigenvectors of the matrix A, and lambda 2 and v2 are the other pair of eigenvalues and eigenvectors for matrix A. We know that. Anyway, if we write matrix D in this form and matrix P in that form, then after you solve this equation, what we can prove is that the solution x of the differential equation can be written in this form, which is very similar, is not very similar, is identical to this type of solutions that we had before for the diagonal equation. Is also true for diagonalizable equations. So the solution x is a linear combination of two functions, and these functions are constructed with the eigenvector of the matrix, exponential corresponding eigenvalue t, and the same here, eigenvector corresponding eigenvalue, exponential eigenvalue t. So this is our main result, and now we are going to prove it in general, and then we are going to solve a couple of examples. So this is the plan. So let's prove this theorem. Proof. And let's start with part 1. Part 1. And to start with part 1, we start with the equation. The equation that we are solving here is x prime function of t is equal a x of t. Okay, but we know that a is diagonalizable, so we are going to put that expression into the equation. So we have x prime still on this side. Over here we are going to have p, the p inverse acting on the vector x. And now that we have this equation, and we did this step because a can be written as p, the p inverse. Okay. So now the first thing we do is, well, we multiply the whole equation by p inverse from the left. P inverse and p inverse here. And then here we are going to have an identity matrix. And now we recall something important, which is that P, the matrix P, is a constant matrix, which means that the derivative with respect to time of this matrix is the zero matrix, and that means this factor can be written inside the derivative, like this. So let's do that. So let's write here P inverse acting on the vector x, all derivative, that is what we have on the left side, and on the right side we have d acting on a vector, and the vector is P inverse x. Altogether, this is a vector now. So what about if we introduce the vector y, which is a function of time, which is going to be the vector P inverse acting on the original variable vector x, x of t. Well, then what we are saying is we obtain an equation for this new vector y, y prime, which is function of time, is d acting on y of t. Well, but here we have for this variable, the equation becomes a diagonal. So here we have a diagonal system. And this is exactly what we call in the theorem equation 2. So you see, and all what we did here, we can go in this way in the calculation and also in that way. So if and only if, so we have proven part 1. What about part 2? Part 2 of the theorem. Well, for that we need the expression of what is D, and this is going to be a diagonal matrix that we are going to call it lambda 1, 0, 0, lambda 2. We know from previous videos that lambda 1 and lambda 2 are eigenvalues of matrix A, and with that we can write this equation explicitly in components if we write y in components, and we are going to write it in this way. We are going to call it the first component y1 of t, the second is going to be y2 of t, and now we can solve the diagonal equation just like we solved the first example in this video, because all that implies, what that implies, that well, we are going to have y1 prime, here we are going to have y2 prime, this is going to be the equation, and over here we have lambda 1, 0, 0, lambda 2 acting on the vector y1, y2, which of course is something very simple, it's just lambda 1, y1, and here lambda 2, y2. So we end up with the decoupled system of equations, which are y1 prime of t is just lambda 1 multiplied by y1 of t, and the other equation is y2 prime of t is lambda 2 y2 of t. And as we said before in the example, the same happens here, of course. These equations are decoupled. And then we can solve them. And the solution is the same that we have in the previous example, very similar. y1 of t is just an arbitrary constant that depends on the initial condition, exponential lambda 1t. And the other function, y2 of t, is going to be another constant, c2, exponential lambda 2 of t. And this is the solution for y. Alright, so now we can write the solution in actual vector form. So let's do it here. Y of t, but now it's going to be vector y of t, is then a vector with c1 exponential lambda 1 t, and here we have c2 exponential lambda 2 t. Okay. Okay, so which one we erase? We erase both, and let's do it again a little bit nicer. There. And here a little bit nicer, more or less over here. Okay, so this is the solution vector for y. And recall, the relation between y and the original variable x is that y, which is a function of time, but it doesn't matter, is equal to p inverse x. So suppose you want to find x here in terms of y, what do we do? Well, we multiply by the matrix P, the whole thing, matrix P, because here we are going to get then an identity. And then we are going to get x in terms of y, and x is going to be P, the original matrix P, multiplied by y. So that's how we compute the original variable. So this is how we transform back from y to x. So let's write down now this equation. So what is x then? X, which is a function of time, is going to be P acting on the variable y of t. We already have y, and we also know what P is. P is the vector, the eigenvector v1, the eigenvector v2, that is multiplying the vector y, which is c1 exponential lambda 1t and c2 exponential lambda 2t. Okay, how we do this product? Well, this product has to be done this column, every component of this row, and the other component of this row. But if we do that, what it's going to end up with is that this number is going to be multiplying every component of this vector, and this number is going to be multiplying every component of that vector. So if you do the calculation, you're going to get exactly what the theorem says we should get, which is that x, let's do it here, x of t is going to be the vector v1, the eigenvector v1 is going to be multiplied all the components of this vector by the constant c1 and by the exponential lambda 1t. And then we need to add the following term, which is the vector v2, and all the components of the vector v2 are going to be multiplied by c2 and by the exponential lambda 2t. And this is actually what we called in the theorem equation 3, and we have proven the theorem. So that is where the equation comes from. So that's it. Then we have proven this result, but this result usually doesn't show up in the literature. It's too long, and and in the literature people like to write a shorter version of this result, and it's down here. What you may find in many textbooks on differential equation is this result here, that essentially say that they are relating the eigenvalues and eigenvectors of the coefficient matrix with the solution of the equation directly. And they say if a matrix 2 by 2 has these eigenvalues and eigenvectors, and the eigenvectors are not proportional to each other, why we have this hypothesis? Well, because with this hypothesis we know that A is diagonalizable. Because we have a theorem in the previous video that says whenever that happens, if and only if A is diagonalizable. And in the previous theorem we have the hypothesis of being diagonalizable, so we already have this hypothesis, but it's not mentioned explicitly. It's here, it's right there. Diagonalizable means these two vectors are not proportional to each other. Okay, and then we relate in the theorem the eigenvectors and eigenvalues with the solution directly. The issue with this theorem is nicer because it's shorter, but it doesn't tell you where the solution comes from. However, in this expression of the theorem, all is written. What we are doing is we're starting with the original equation, we are changing the equation by this transformation into a diagonal equation, then we solve the diagonal equation and we transform back. So we are going to see how all these ideas work now in a particular example. The example we have in mind is the following. Solve this system of equation for this matrix A, which we know from a previous video is diagonalizable. So how do we solve this problem? Solution. Well, let's recall what we know about matrix A. So recall, I'm gonna put it a little bit higher up so we have more space there. So recall. Matrix A, we know that is diagonalizable, so it can be written as PD P inverse, and we know that also with matrix P. What is matrix P? matrix P, we know the eigenvectors of this matrix is 1, 1 and negative 1, 1 from my previous video, and D is 4, 0, 0, negative 2. And again, the reason is that is because there are some things here. Okay, there, now they go away. Because what? Lambda, the eigenvalue, is 4, and an eigenvector, for example v1, is 1, 1. That's why we have that column in matrix P. And lambda 2 is negative 2, and we have an eigenvector, the corresponding eigenvector, v2, is negative 1, 1. And that's why we have the other column in matrix P. Okay, so now the short theorem says, oh, you know all that about the matrix. Then you got your solution, because the formula in red on the top of the screen says that the short theorem short theorem is going to say that x of t, all the solution of this equation can be written as a linear combination C1 of the vector 1, 1 exponential 4t plus C2 the vector negative 1, 1 exponential negative 2t. It's a little bit cramped up. So that is what the short theorem is telling us. We already have the solution and we are done. That's it. And when we know what we are doing, this is what we are going to do. And we should end here. That is what we wanted to do. We use the theorem and it's done. But let's write down a little bit more, rewrite a little bit the solution. So let's write it down in the old way. So this is the vector form. Now let's go back to the old way, because I want to emphasize something here. X of t is actually, well, we need to multiply this by the components, this by the component, the same here, and we get something of the form C1 exponential 4t, and down here we get, first of all, this is a vector with component x1 of t. I'm getting ahead of myself. X2 of t. Okay. And now from the solution, we know what x1 and x2 look like. C1 exponential 4t, and here C1 exponential 4t, and to that we need to add the vector negative C2 exponential negative 2t, and then C2 exponential negative 2t. This is the other vector. Okay. And now what? Well, now we put everything together and then we get that x1, the solution, first component of the solution is going to be C1 exponential 4t minus C2 exponential negative 2t, and the other solution, x2 of t, is going to be C1 exponential 4t plus C2 exponential negative 2t, and C1 and C2 are arbitrary constants. Okay, and this is the solution, but recall that this is the solution to the following system. The system is x1 prime is equal x1 plus 3x2, and x2 prime is 3x1 plus x2. This is the solution of this system of equation. Okay, so because this system is actually the system x prime equal 1, 3, this is our coefficient matrix, recall, x. So the theorem says this is the solution, therefore these are the solutions of this system. That looks strange because the system of equation has coefficients 1, 3, 3, 1, and there is no 3 anywhere around. It looks a little bit, going from the equation to the solution, it looks a little bit like magic. So to understand that this is not anything magical, that's why we have the long theorem and the long proof, because this is how we understand how we can find these solutions for these equations. So let's go back to the equation. Let's go back to this equation here, the original equation. Let's copy them and let's put them over here. Suppose you want to solve this equation. We know that we cannot solve this equation one at a time because they are coupled, isn't it? Here we have x2, and in the second equation we have x1, so they are coupled. Okay, but let's recall now. So we are stuck, isn't it? Okay, but let's recall theorem 1, our first theorem, the long version of the theorem. We said over there that oh, by the way, well, we say over there that y, everything can be solved for this variable y, which is p inverse acting on x. And what is p inverse in this case? Well, we have matrix p. What is matrix p? Matrix p is over here. It's not difficult to see that we are going to have this matrix. We need to divide by the determinant. The determinant is 2. So we have done this before. So this matrix is 1/2, 1, 1, don't change sign. This one do change sign, acting on the vector x1, x2. And one thing here that I would like to emphasize is we are doing all this to show that there is no magic here. So what are the components of y in this particular example? Well, y1 is going to be 1/2 x2 plus x1. And y2 is going to be 1/2 x2 minus x1. You see what I did? I just did this multiplication and I got that, and this multiplication and I got that. Okay, so these are our new variables. So the system should be diagonal for these new variables. So the variables involve adding the two old variables and subtracting from x2 x1. So this here is giving us the directions what to do to the equation. What we need to do here is simply add the two equations, and it should be decoupled. Then let's see if it's true. What happens if we add the equations? If we add the equations, we are going to get x1 prime plus x2 prime. And on the other side, what do we get? Well, we get 4x1 and also 4x2. Okay, but that means that x1 plus x2 all prime, so the variable addition, derivative of that, is 4 times itself. x1 or x2 plus x1. So, and the same happens if I divide by 2, the whole equation. Let's make a little bit of space here. If I divide by 2, the same happens. So what we have found out is, I call y1 to be this quantity. So what we found is that y1 prime is actually equal 4y1. Interesting. So the equation is decoupled for this variable y1. And what happens if we do this operation here? Okay, so let's copy again the system. Copy. Let's put it somewhere here. Maybe, yeah, over here is good, or yeah, over here. And now what we need to do is we need to multiply by -1 the first equation, so this one, all the equation, and then add the second equation, and the result is going to be the following. We're going to have x2 prime minus x1 prime, and on the other side we are going to have 2x1, because we have a -1 plus 3 is 2, and then on the other we are going to have ground color, we are going to have -2 x2. So if we write this in terms of x2 minus x1, what we get here is x2 minus x1 all prime, and here we have a 2, but I want x2 positive. I want x2 positive minus x1, so I need a negative here, and now I can divide by 2 if I want, but I'm gonna need to move this a little bit away. And now we have our second variable, which is y2. So what we get here is that y2 prime is actually -2 y2. So we have decoupled the system for this by doing the operation that is, by doing the operation that they are indicated here. So in other words, the eigenvectors, recall these are the components these here are the components of the eigenvectors of matrix A. The eigenvectors of matrix A are telling us how to decouple the original equations. The information here allows us to decouple the equations. So now it's very easy to find the solutions. We have done it before. We can do it one more time. The solution for y, solutions. The solutions are, well, y1 of t is of course some constant exponential for t, and y2 of t is some other constant exponential -2t. So here are the solutions of the diagonal system. Now how we transform back? Well, let's recall what the y's are defined by this expression. Copy. Let's put it here somewhere. I have the y's. Now how I get the x? Well, you see here, if we add up these two equations, the x1 disappears and we get x2. And if we multiply by -1 here and plus, and then we add up, then the x2 disappears and we get x1. So these equations say very easily that x1 is going to be y1 minus y2, and x2 is going to be y1 plus y2. Well, we got our solutions for x now. And this is why we have the solution that we got before. x1 of t has to be y1, which is up here. It's down here. This is y1. So is c1 exponential for t minus, because we need a minus here, minus c2 exponential -2t. And the other solution, the other function, x2, the solution is c1 exponential for t, this time plus c2 exponential -2t, which is the solution we've found before by magic, and now we find it by calculation, by decoupling the system with the information of the eigenvectors. And from here we get the solution in vector form, of course, which is c1, the vector 1 1 exponential for t, plus now we have c2, and now we have a vector -1 1, and then we have exponential -2t. So this is another way to solve the same system, a little bit longer, but we see where the solution comes from. There's no magic. Is decoupling the system with the formation provided by the eigenvectors. This theorem we've been discussing so far can be generalized from 2x2 system to n×n systems. And here is the short version, the generalization of the short version of the theorem. If we have a matrix A that is n×n and is diagonalizable, and it has the following eigenpairs, lambda 1, v1, and now we need to have n eigenpairs, lambda n, vn, because the matrix is n×n. Then if these eigenpairs exist and matrix A is diagonalizable, then all the solutions of this system, which is an n×n system, are given by linear combinations of these functions here, which are constructed in the same way as before, the eigenvector times exponential corresponding eigenvalue times t. All terms are given in the same way. So a couple of remarks. Each of these functions, so it can be written as in this form, xk, the k function is going to be the k eigenvector and exponential eigenvalue kt, and all them together, k from 1 to n, all together they are called fundamental solutions of the equation, of this equation. You need now n solutions to have of this type to have fundamental solutions, and of course this equation here, which is equation 2, is now called the general solution for this case. And it's clear that each one of these solutions, each one of these terms, so each one of these is actually a solution of the differential equation, but is useful to actually do the calculation. Each one of these functions constructed in this form is a solution, but is at least once we have to do the calculation to see how this works. So we have the function x is the function, the kth function, which is a function of time, and suppose we compute the derivative of that. So I want to see that this function is a solution of this equation. So what I'm going to do is I'm going to compute the left side of the equation, the derivative. Then I'm going to compute the right side of the equation, the a acting on that, and then I'm going to check that they are exactly the same. So let's compute the derivative. What is the derivative of that? This is a vector k, which is constant vector exponential lambda kt, and we are computing the derivative of that. But the vector is a constant vector, so we can pull it outside the derivative. And we need to compute the derivative only of the exponential lambda kt, which we know what that is. That is going to be, we drop a lambda k, we still have the vector, and then the same exponential lambda kt. Okay, what is the other term? The other side of the equation is a acting on that solution, the solution k, function of t. Well, is a acting on the solution, and the solution is a constant vector times a scalar function, exponential lambda kt. So this is a scalar function, so I can just compute a acting on the vector, okay, and all that multiplied by the exponential lambda kt. But this vector is an eigenvector of the matrix A, so we have lambda k v, the same vector, exponential lambda kt that was outside all the time. Then it's easy to see that we got a solution because both sides are equal, and then x k prime is equal a acting on k. So that was the end of the check. And that's why this type of functions which are constructed with an eigenvector of the coefficient matrix and exponential eigenvalue of the same matrix, they are always solutions, because the derivative here drops a lambda, and A acting on the vector drops another lambda, and then you obtain a solution. We end this video with one more example. Unfortunately, we don't have time to solve it. The example is solve a system of equations with this matrix, and now we have some initial conditions, and now we are going to use the short version of the theorem to solve it. Essentially, here is the solution. You can read it, but essentially the question is the matrix diagonalizable? In this case it is, because in order to verify whether it's diagonalizable or not, we need to compute the eigenvalues and eigenvectors. If you do, you are going to find these eigenvalues and eigenvectors, so yes, the matrix is diagonalizable, and here you have everything you need to construct the solution. Short version of the theorem. Now the initial condition is going to fix the constants C1 and C2, and the calculation is here, so you can pause the video and take a look. You can solve it yourself first, and then compare with the solution in the video. And with that, we finish our video today. I hope to see you guys in the next video.